Hi, welcome to our 25th lecture in graduate combinatorics. Today we'll continue our discussion about trees, and we will give the first proof of this famous theorem attributed to Cayley, but which was also proved by Borchardt, stating that the number of labeled trees on n vertices equals n to the power n minus 2. Our first proof will involve proofer codes, which are a very useful and convenient way of encoding labeled trees on n vertices. So let's recall the definition of proofer codes. Say we're given a tree T, which is a label tree on n vertices, and let's assume that the vertex set consists of the numbers 1, 2, up to n, which we denote by n between square brackets. So we start with T1, which is our tree T with n vertices. And in the first step, we denote by B1 the smallest leaf in T1. So in our tree on the left, the smallest leaf is this one. So this is going to be B1. And so we list it here as 2. And we denote by A1 the neighbor of this leaf. And that neighbor is 1. Okay. Now in the next step, what we're going to do, now we delete this way. So this is the first step. This is a step. Second step, T2 will denote T without a leaf, B1, and is a tree on n minus 1 vertices. So that's an important property here. When you delete a leaf from a tree, you get another tree. And we repeat the procedure. We denote by B2 the smallest leaf in T2. And for our graph, that will be 3. So B2 equals 3. And we write that in our table, and we also write down the neighbor of B2 in the tree T2, which is 1 again. And so the procedure continues again. You have a third step, and the smallest leaf now will be 1, and so that's B3. So we put the 1 there, and its neighbor is 4, and it goes on like this for n minus 2 steps. So in this case, n equals 6. So we have 4 steps. So in the last step, we have the leaf is 5. So that's B4. And the neighbor adjacent to it is 1. It's 4. I'm sorry. It's 4. Okay. And so the tree T is encoded by this 4 tuple, which is 1, 1, 4, 4. Okay. Now, before we go and we show that this correspondence is a bijective correspondence between labeled trees on n vertices and order n minus 2 tuples with entries from 1 to n, let's just observe a few things about this procedure and about the entries in the vectors A and B. So note, if we look at starting from the left, if we look at the pairs A1, B1, so you have this edge 1, 2 or 2, 1. So that's an edge of the tree. And then the next pair is 3, 1. That's another edge of the tree. The next pair is 1, 4, another edge, and 5, 4. So here we have, so in this table of 2 rows, A and B, the columns give us you get these n minus 2 columns give us n minus 2 edges from the tree. But the tree has n minus 1 edges. So what is the last edge? Well, the last edge, we can deduce it from our procedure. In the last step, as you look on the top row, we have eliminated 2, 3, 1, and 5. So at the last step, because we have eliminated 2, 3, 1, and 5, you know that at this last step, the remaining tree is of the form 4 and 6. And we know, so it's implicit from this procedure, the entry on the top row, that's going to be 4, because that's the smallest leaf. And also implicit in this table is the entry on the on the second row, which is the neighbor, which is 6. So this 6 is kind of like the entry an minus 1. And that will be always the case that this an minus 1 entry is always n. So you might as well omit it. So it's a very clever encoding procedure. And so you get this n minus 2 tuple. Now, let's see why you can go backwards. So I'll give you a sketch of the proof that the correspondence T goes to this proofer code is a bijection between the set of label trees on n vertices and this Cartesian product n times n and so on, n minus 2 times. And to do that, we show that this map is invertible. So from a tree, we get a unique, you get a unique code. That's pretty clear. What I want to show you is if you're given an order n minus 2 tuple of the form written below, a1, a2, an minus 1, there is a unique T label tree such that a of t equals a. So you can reverse the procedure. You can reverse the procedure, and from any n minus 2 tuple, you can get a tree associated. So how does it work? Well, so let's look here again on what we did when we calculated the proofer code. You see, in the top row, the entries never repeat because the top row keeps track of these leaves that we delete. So once, for example, the first entry 2 is in the top row, it never appears after that because it's deleted from all the subsequent trees. So the top row contains distinct entries, and those distinct entries actually, so you have n minus 2 distinct entries, and then you'll have another one, an n minus 1 entry at the end, like the 4 we have there. And those entries together with the element n, they will be the vertex set of the tree T. Okay. So if you, what I'm saying here again is that if you take these elements from there with the 6 from here, they give you the vertex set of the tree T. Similarly, in T2, the vertex set of T2, so vertex 2 is deleted here. So the vertex set of T2 will consist of these vertices together with the 6 from the end, and so on. So that's how you can keep track of the vertex sets of these trees at each step. The vertex set of T3 will be again 1, 5, 4, and 6, and so on. Okay. Now, at the moment, so what can we say about the procedure? So if we were to be given some kind of sequence, like let's say n equals 7, 2, 2, 4, 1, 7, and so on. That's our code, and we want to figure out a tree that corresponds to it. So in the first step, all the vertices except these ones, a1, a2, an minus 1, were available to be chosen. And so we choose the smallest of them. So B1 is the minimum of all x that do not belong on the second row. So as you see here, at this step, these are the elements in the second row, and B2 is the smallest one that does not belong in that set. Okay. So in our situation, what would be so this B1 from here goes in this position. This is the B1. And in our situation here, what is the smallest element that doesn't belong on the second row? That's going to be 3. Okay. So that gives us the first edge. We have an edge between 3 and 2. Okay. Now, what happens at the next step? So at the next step, the vertex, so we go back and forth between the construction and the kind of backwards construction. The next step, the vertex 2 has disappeared. Okay. So now we are in this tree T2. Okay. So vertex 2 can be ignored. And we are choosing the smallest available, smallest leaf at that time. And we cannot choose elements from, you know, this second row. So, and we cannot choose this element too, because this one has disappeared. So the choice is 3. That's the element that we have to pick. So in our situation, in the second step, what we have to do is we have B2 is going to be the minimum of, let's say, y, such that y is from the set n. But what we cannot pick? We cannot pick B1 because B1 is gone already. And we cannot pick A2, blah, 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 all the way to AN minus 1. So by the way, I added AN minus 1 here as at the end as n. This is n. Okay. So in our situation, in this example, so B1 is 3, and then we have 2, 4, 1, 7, 7. So what's the smallest number that is not in that set? So I think that is going to be 5. Okay. And then the procedure continues like that. You have B3 is the minimum element Z, such that Z belongs to N. But it cannot be, you cannot choose B1 and B2 because they're gone, and it cannot be equal to A3 AN minus 1. Okay. So you see in this situation, we cannot choose 3 and 5, we cannot choose 4, 1, 7, 7. So we have to choose 2. And we continue like that. And then you can go all the way to Bn minus 1, which is the minimum of, let's say, W belongs to N, minus, we cannot choose B1 all the way to Bn minus 2, union AN minus 1. So let's see how it works here. The entry above 1, we cannot choose 2, 3, 2, 3, 5 from before. We cannot choose 1, 7, 7, so that entry is 4. And then we cannot choose 3, 5, 2, 4. So we have to choose 1. And then the last one is going to be, I think, 6. Okay. And so this gives us, if you were to build a tree, you have the vertex 2, you have adjacent to 3, adjacent to 5, it's adjacent to 4, which is adjacent to 1, adjacent to 7, and adjacent to 6. Okay, so this is the tree that we get for, and you can check it, double check that by applying the procedure in the proof of code encoding, you get this tree. So now, because this correspondence is bijective, this argument here, this theorem, implies that the number of labeled trees on n vertices is the same as the number of proof of codes, and the number of proof of codes is clearly n to the power n minus 2, and so that proves the theorem. In the notes on the Google Drive, I give another proof of this result using inclusion exclusion, and I invite you to read it. It's a very nice proof. What I want to do now is go towards a generalization of Cayley's theorem, which is called Kirchhoff matrix tree theorem, which counts the number of spanning trees of any graph with vertex set 1 to n. So to do that, I need to define a few things. And so let me start talking about changing the topic a little bit. And I'll talk about what is called a Laplacian matrix. Laplacian matrix and incidence matrices for a graph. Okay. So let's say we're given a graph. I'll do the graph as in the example in the notes. So with vertex set V and edge set E, and let's just say the vertex set is 1 to n. Okay. Now I will define first the directed or oriented incidence matrix, and to do that, let's say that from this graph, what we do is, let's say we assign an orientation to each edge. So if you have an edge, let's say like this, when you assign an orientation, the edge, maybe let's say you have vertex X and you have vertex Y, and let's say you have this orientation XY, what it does, it puts some kind of order on the vertices, and this X is called the head, the Y is called the head, and X is called the tail of the I'm getting it messed up. Okay, we'll figure out. So this is the head, and that's a tail if you do this order this way. So let's say we put an orientation here. So let's say we orient 5 to 1, 1 to 2, 3 to 2, 2 to 4, 4 to 3, and 4 to 5, and I have, yeah. Okay, so let's say I put orientation to it. So given an orientation of the edges of gamma, so let's call this orientation, let's give it some name, let's say sigma. We define its oriented, so the unoriented or directed incidence matrix of gamma as follows. So this matrix, let's give it a name. It's called N. So this matrix, N, as rows will have the vertices. Okay. And columns are the oriented edges. Okay. So in our example here, this N for this will have the rows, let's say 1, 2, 3, 4, 5. And then I can put the column, the edges 1, 2, 1, 5, 2, 3, 2, 4, 3, 4, and 4, 5. Okay, these are the edges. I mean, I don't put the orientation in them, but that will play a part in a second. And now the entry are as follows. So it's similar to the matrix that we defined before when we did handshaking lemma. In the column of 1, 2, we put 0 for every vertex that's not involved in 1 and 2. And we put a +1 at the tail, and we put a -1 at the head. Okay, so it goes from positive to negative, from tail to head. And we do the same thing for each edge. So for example, 1, 5, so 2, 3, and 4 are not involved, so that's 0, 0, 0. And then it's oriented from 5 to 1. So in the 5, we put a +1, and in the 1, we put a -1. Similarly, 2, 3, we have a 0 at position 1, 0 in position 4, 0 in position 5. And 2, 3 goes from 3 to 2, so we put a +1 in 3 and a -1 in 2. And 2, 4, we have a 0, 0, 0. And 2, 4 goes from 2 to 4, so we have a +1 and a -1. 3, 4, we have 0, 0, 0. And it goes from 4 to 3, so it's a +1, -1. And 4, 5, it's 0, 0, 0, +1 and -1. Okay, so this is, you can think of this matrix as taking the usual incidence matrix that had just zeros and ones, which we used when we did the handshaking lemma, and you take each column and you see, so here we're not going to have loops. So whenever you see each column, that corresponds to an edge, and that edge has two distinct endpoints, and in the entries corresponding to those vertices, you will see ones in the usual incidence matrix. And what you do, you flip one of those ones to a -1. Okay, that's exactly what happened. So each column will have a bunch of zeros, some +1, some -1, and that's it. Okay. Now we say unoriented matrix because there are many such matrices. First of all, you can label the rows. I labeled here 1, 2, 3, 4, 5, and I label the columns 1, 2, 1, 5, and so on. But you can write them in different orders, so you'll get different incidence matrices. And also, the number of orientations, it's easy to see that you will have 2 to the power the number of edges orientations of a graph gamma, because every edge you can orient it in two ways. So you have many incidence matrices. Okay, but they will all have very interesting properties. So let's go discuss those properties. Before I do that, let me give you a quick definition. So given a graph gamma, I mean, we did this before. Let me recall that a spanning subgraph of gamma is a subgraph of gamma whose vertex set is V. Okay, so just remember that that's what a spanning subgraph is. And so with that definition, there is the following, we have it allows us to define the following notion: a spanning tree of gamma is a spanning subgraph of gamma that is a tree. Okay, so in our situation, if we have this graph here, let's see how it was done this way: 1, 2, 3, 4, 5. Let me draw a couple of subgraphs. So this one, 1, 2, 3, 4, 5, is a spanning subgraph, but not a spanning tree, because it contains a cycle. But, this one, 1, 2, 3, 4, 5, this is a spanning tree. There are others. This one, 1, 2, 3, 4. This is also a spanning tree. Okay, so there's several spanning trees for this graph. Okay, so well, I want to do this detour because I want to mention that the theorem that we proved before, that the number or label trees on n vertices equals n to the power n minus 2 can be rephrased as saying that the number of spanning trees of the labeled complete graph on n vertices is n to the power n minus 2. Okay, so it makes sense to actually, this is about the number of spanning trees of a very nice graph, which is the complete graph on n vertices. So one can define for given a graph gamma, we can define tau of gamma, which is the number of spanning trees of gamma. Okay, and this theorem again from Cayley and Borchardt theorem. Theorem, which is this one here, is the same thing as saying that tau of kn equals n to the power n minus 2. Now there's some simple properties of this parameter. For example, tau of gamma is positive if and only if gamma is connected. And something also obvious, tau of gamma is 1 if and only if gamma is a tree. Okay. These are fairly simple properties. And you can calculate it for some simple graphs. For example, what is tau if I give you the cycle on n vertices? Well, the cycle, if you delete any edge, you get a tree. So that gives you the number of spanning trees, that's n. But you can ask yourself, what is the number of spanning trees of the Peterson graph and so on, of any other graph? And that's what we're going towards. We will prove a theorem of Kirchhoff, which gives a very nice formula for the number of spanning trees of any graph. To do that, we need to build up a little bit of notation and some more notions. And so let's prove the following proposition. So now we're coming back to the incidence matrix. So let's say let gamma be a graph on n vertices and n be a directed incidence matrix of it. Okay. Now, here are the things that we want to prove. First, the rank of n is always the same, regardless of what incidence matrix we pick. It will equal n minus c, where c is the number of components of gamma. So in particular, as a let's put it as 1 prime. The immediate consequence is that gamma connected implies that the rank of n equals n minus 1. And it's actually, okay, it's a if and only if situation. Okay. 2, the matrix n is what is called totally unimodular, which means that any square submatrix of n has determinant 0, +1, or -1. Okay. And the third one, it's a bit more involved. Assume that gamma is connected. Okay, so the rank of this matrix is n-1 by the previous step. Then let's take at f be a subset of n-1 edges of gamma. Okay. Now what we are going to do, so the way to think about what happens here, so we have this matrix. So you have, this is n. We have the vertex set here. So you have vertices 1, 2, up to n. And now by nf, okay, denote by nf, the n-1 by n-1 matrix. And it's not the, it's un. We'll see in a second. Matrix, submatrix of n, okay, where the columns correspond to the edges of f. So f has n-1 edges. So these edges, maybe they're spread out all over, I don't know. Let's say in this picture there are 3 of them. So that would be f. So you keep those columns. So you keep those columns, and you remember that cardinality of f is n-1. And then from the rows, we keep n-1 row. So we kind of, let's say if I keep the first, n-1 will be something like this. So we get, so the columns correspond to the edges of f, and the rows are, so the n-1, the columns correspond, the rows correspond to some n-1 vertices of gamma. Okay, so we have this square matrix where we have the columns that correspond to the edges in f, and we pick n-1. So we want to have a square matrix. So it's n-1 by n-1. Now what we want to prove is the following, is that nf is invertible if and only if the edges of f, the subgraph of gamma induced by the edges of f, so the edges of f induce a spanning tree. You have n vertices and you have n-1 edges. So sometimes n-1 edges will give you a tree, but that doesn't have to be the case all the time. But here we have an equivalence between this combinatorial condition. We are picking n-1 edges from the graph. And saying, okay, this the subgraph, which has the vertex set of gamma 1 to n, and it has these n-1 edges. This subgraph is a tree if and only if this matrix, this sum matrix of the incidence matrix nf, is invert. Okay, so let's try to prove some of these. Okay, some of these things. Okay, let's see how it goes. Okay, so the first one is that the rank of n equals n minus c, where C is the number of components. Okay. Now, here's the thing. If we have, let's say, gamma 1, gamma 2, gamma C, if these are our components, so we have no edges between them. Okay. Okay, in N, I can label the vertices in a certain way and the edges a certain way, but I can rearrange the rows and the columns. But let me rearrange it such that the vertices of gamma 1 come first, okay? And then they're followed by the vertices of gamma 2 and all the way followed by the vertices of gamma C. If you permute rows and if you permute columns, you're not going to change the rank, okay? So I'm not changing the rank. Then I can permute them such that here, so here I have vertex set of gamma 1, vertex set of gamma 2, vertex set of gamma C. And then I can put the edges of gamma 1 first, then the edges of gamma 2 second, and all the way here, edges of gamma C at the end, okay? Now, because there are no edges in between these components, there are no edges between gamma 1 and gamma 2. So here, I will get zeros. Okay, 0, 0, 0. Okay, so it's kind of like a block diagonal matrix, kind of. So, and what do we get here? So here, we will get an incidence matrix of gamma 1. In this block here, we will get incidence matrix of gamma 2, and in the block here, this would be an incidence matrix of gamma C. Okay, and what will be so what happens is that the rank of the incidence matrix N will equal the rank of, let's say, N gamma 1 plus all the way plus rank N gamma C. Okay, now each of these components, so inside here, okay, each of these components are connected subgraphs. So what essentially happens, so in 1 prime, we had this result that rank of N is N minus 1 if and only if gamma is connected. So actually this result 1 prime is equivalent to the general result that rank N is N minus the number of components as follows. If you assume 1 prime, which we'll prove in a second, then the rank of N gamma 1 will equal the number of vertices in gamma 1 minus 1. And similarly, all the way to the rank of gamma C will equal the number of vertices in gamma C minus 1. And when you add up all these numbers, what we will get is the number of vertices in gamma 1 plus all the way plus the number of vertices in gamma C minus 1 for each of them, which is C. And together, this will give us N minus C. Okay. So it's sufficient for us to prove that the rank of N is N minus 1 if and only if the graph is connected. Okay. So now let's prove that. Okay. Well, so let's let's make the following observation. So let's look at this example. If you look at this matrix, on each column, you see a 1 and you see a -1, okay? So if we add up all the rows, we get a 0, okay? So that should be clear. So, so we have our matrix N. Now, you know that rank of N is dimension of row space, okay? And it's the same thing as dimension of column space. If we look at the, like I said before, as a row space, if you take, let's say this is row 1 all the way up to row N, row 1 plus all the way up plus row N equals a 0 vector. And let's put 0e because it has cardinality E entries in it. So that implies that the set R1, Rn is a linearly dependent set of vertices of vectors. And so the dimension of the row space of N is at most N minus 1. Because it cannot be N, because these are linearly dependent, so is at most N minus 1. Okay. Now, how do we prove? So what I want to prove, let's prove the implication that if gamma is connected, that implies that rank is N minus 1. So, well, so what can we, so let me see here. So what we're looking here is we're trying to figure out, it's essentially an application of rank nullity theorem. Okay. Because we're trying to figure out what the rank is, and the rank plus the nullity of the matrix N equal N. And so we're trying to figure out what's, if I have a vector, let's say alpha 1, alpha N, and I multiply by this matrix N, and I get the 0 vector E. So this is row 1, blah, 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 row N. What can I say about this vector alpha 1, alpha N? That's basically what we're doing. And how does this work? Well, so we have this alpha 1, alpha N multiplied by the incidence matrix N, which is R1, Rn, and this is the 0 vector. So that's the same as alpha 1, R1 plus alpha N, Rn is the 0 vector. Okay. And we don't want, so let's just, you know, alpha N are not all 0. Because if they're all 0, there's nothing to worry about. Okay. So let's assume they're not all 0. So let's take J, so from 1 to N, such that alpha J is not 0. Okay, so what happens here? So we have this vertex J. So alpha J multiplied by its row, okay. So this is the row J, and you see from the top, you have a bunch of edges, okay? You will have a bunch of edges. If J is not contained in that edge, that entry is 0, okay? But if J is contained in that edge, let's say F, then the entry here is plus or minus 1, okay? So what happens here is, so we assume graph is connected, so there's at least one edge, F, where J is contained. So let's say we have a vertex J, some edge F, and there's another vertex K on the other side, okay? Let's say alpha K here, and this is RK, this is RJ. And you can, let's assume without generality that here this is a +1 and this is a -1. It works the other way as well, but okay. So what do we have here? If you look at this sum, alpha 1 R1 plus blah 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 plus alpha n Rn equals 0. If you look in the entry corresponding to the edge F, like this entry here, okay, there are only two non-zero values of, in the matrix N. Those are corresponding to the to these vertices J and K, okay? So because alpha 1, so in the entry corresponding to the edge F, so in that position, everything is 0 except in alpha J Rj plus alpha K Rk. So all the other, the entries in the other rows are all 0. So this is in that column corresponding to edge F. So that has to give us 0 in that position corresponding to F. So how can that happen? Well, in Rj, we get a +1. So that's alpha J times +1. And on the other side, we get plus alpha K times a -1. And that's 0. So that implies that alpha K equals alpha J. Okay. So it means that the entry alpha in the vertex J is equal to the entry of alpha on this vertex, which is adjacent to it, K. And that will be true for any vertex that's going to be adjacent to J, any other vertex, I, J, K, and so on. And then you can repeat the procedure starting at these vertices. You know, the entry of alpha, it's the same on the vertex K as it is on its neighbors, and so on. So if you repeat that procedure, what it does, it tells you that alpha 1, they're all going to be equal to each other. So all the entries in alpha are the same. And it means that the only linear combination of rows that gives you 0 is the one that we discussed before, where you add them up. So that tells you that the dimension of the row space has to equal n-1. There are no other possible linear combinations of these rows that give you 0. So from here you get that rank of n equals n-1. And once you know that the graph is connected, the rank is n-1, the reverse implication is easy. So I'll leave that as an exercise. And I think I'm out of time for now. So next time we will prove the remaining parts of this proposition, and we'll go towards. So let me just state before I go, Kirchhoff matrix tree theorem will give us a formula for tau of gamma, the number of spanning trees. Very nice formula as a function of what is called the Laplacian matrix of gamma. The Laplacian matrix of gamma, it will be an incidence matrix times its transpose. You will see in, next time that it doesn't matter which incidence matrix we pick. The incidence matrix times transpose, it always equals the same thing, and it will equal the diagonal degree matrix of gamma minus A, which is the adjacency matrix of gamma. Anyway, we'll talk more about them in the next lecture.